posture. So for today's presentation, we're going to be presenting a practical overview of post-quantum cryptography. We'll walk you through what PQC is and why it's needed. We'll also touch base on some concepts of quantum computing, go over the selected PQC algorithms, and then we'll end with some practical information for implementing PQC in SSH and HTTPS services. And we also hope that after this presentation, you guys will be motivated to start your own path to implementing your own PQC on your systems.
But before we begin, I'll give a quick introduction about myself. Hi, my name is Maria Ramirez. I'm currently a second year at UC Berkeley studying applied mathematics and data science. A few things I'm a part of is WICS, which is the Women in Computing and Data Science Club, where I'm the project's committee member as well as the marketing chair. I'm also an MPS Scholar Mentor, where I mentor undergrad students who are majoring in STEM-related majors, as well being a part of the CalTeach program, where I am a teacher assistant at elementary schools teaching kids about math.
Hi, I'm Adam Ramirez. I'm a third-year applied math major with an emphasis in CSC, attending UC Merced. Some things I'm a part of on campus is the SCaLE program. I'm a SCaLE research intern, which stands for Students Assessing Teaching and Learning. Along with that, I'm also the president of the ACM chapter at UC Merced, which is the Association for Computing Machinery. And at UC Merced, I also presented some workshops on PKI, Linux, and cybersecurity. So to start off, what is post-quantum cryptography? I provided a little definition over here. It's cryptography focused on developing encryption algorithms that can run on classical computers, but withstand attacks from future quantum computers. I also provided some other ways PQC is referred as quantum safe, quantum resistant, and quantum proof encryption. So PQC algorithms are based on mathematical techniques that are believed to be too difficult for quantum computers to solve. So although quantum computers will be powerful enough to break current encryption algorithms, they don't fully exist yet. However, security experts say that it's important to plan ahead, in part because it takes years to integrate new algorithms across all computer systems. So why do we need PQC? I provided 3 points of why we need it. First is we need to future-proof our data and communication from quantum threats. PQC gives us the next generation encryption algorithms that will remain secure now and after quantum computers come online. Second, it will protect our data from quantum attacks. Quantum algorithms such as Shor's algorithm and Grover's algorithm, which we'll get more in depth along the presentation, are known to break or weaken our existing encryption algorithms that we rely on daily. Most notably RSA, if you guys know what that is. For instance, we want to make sure our online privacy, banking, and crypto wallets are secure from quantum computers. And lastly, for compliance purposes. NIST, or National Institute of Standards Technology, is already planning on deprecating current algorithms over the coming years. So it's a good practice in adopting security-related standards. In regards to quantum threats, harvest now and decrypt later is one of our biggest quantum threats. So harvest now and decrypt later is when bad actors and nation states are collecting encrypted data in hopes of decrypting the data once quantum computers come online. So by migrating to PQC algorithms now, we can prevent this attack in the future. And you're going to see a repeated pattern of us reminding you guys to implement PQC algorithms now instead of later. But before we dive into cryptography, I'd like to address one misconception, which is post-quantum cryptography is the same as quantum cryptography, which is wrong. They're not the same. So the difference is post-quantum cryptography, like I said at the beginning, is using classical encryption algorithms resistant to quantum computers. Where on the other hand, quantum cryptography is encryption algorithms using quantum computers. Now, Marie will give you guys a quick introduction on cryptography.
So before we get into talking about quantum cryptography, let's talk about classical cryptography. In general, cryptography is a practice of using math to protect information so that only intended recipients can access it. Whereas encryption is using specific cryptographic methods to convert data into a scrambled format. So the cryptography methods that we're interested in can be divided into 3 different types. First, we have symmetric encryption, which uses a shared key. Second, we have asymmetric encryption, which uses both a private and a public key. The public key is used to decrypt a message, and the private key is used to decrypt a message that was encrypted with the associated public key. And lastly, we have hashing functions, which are one-way functions that provide data integrity. So let's take a look at symmetric encryption. In this scenario, we have the famous Alice and Bob used in cryptography. As stated earlier in symmetric encryption, a shared key is used to encrypt and decrypt a message. So Alice and Bob meet somewhere and exchange a key so that they can communicate through secret messages. Alice has a message that she wants to send to Bob. She uses the shared key to encrypt her message. In today's world, she's most likely using AES 256 algorithm. The AES algorithm became a standard back in 2001 by NIST. It superseded DES, however, 3DES is still used in chip cards used because of legacy applications. Now back to our process. The encryption data creates a ciphertext of the message. At this point, if a bad actor, Eve, intercepts the message, she will not be able to access the original text. Bob will receive the encrypted message using the shared key, can decrypt it, and thus read the message. Although the process worked out nicely, the only problem with symmetric encryption is the process of sharing the key. There's really no secure way to share the key when Alice and Bob are located in different locations. So let's say if Bob is in Europe and Alice is in the US, it's not always practical to have either one travel to exchange the keys. But we'll see the solution to this problem with asymmetric encryption. So in asymmetric encryption, we'll use the same scenario with Alice and Bob, where we have Alice wanting to send a secret message to Bob. The main difference from symmetric encryption is that asymmetric encryption uses 2 keys, a public and a private key. The public key is used to encryption, whereas a private key is used for decryption. As another message she wants to send, Alice has another message she wants to send to Bob. In our asymmetric scenario, both Bob and Alice have created their own key pair, a private and a public key. They both publish their public keys on the internet. This allows anyone that wants to send encrypted messages to them use their public key to encrypt the message. As you can see, asymmetric key encryption eliminates the problem of using the shared key. In today's world, she most likely will use RSA 2048 algorithm, or more recently, elliptical curve cryptography, known as ECC. The RSA 2048 encryption process will generate a ciphertext. Bob receives the encrypted message, so he uses his private key to decrypt the message, and then is able to read the original message. So one thing to note, asymmetric encryption is slower than symmetric encryption for large chunks of data. This is why, in practice, asymmetric encryption is often used as a method to securely exchange symmetric keys. So once both parties have shared the key, they will use the shared key to decrypt and encrypt message thereafter. So the last encryption method I want to mention is hashing functions, which on the other hand are not encryption algorithms, but rather a one-way mathematical algorithm. It takes data of any length and converts it into a fixed length string called a hash value. It essentially creates a fingerprint of the data. It provides a way to verify the integrity of data or if the original data had been modified at rest or during transit. So as we see in the diagram, we start with the plain text message. Then we apply the SHA-512 hash function, which gives us a unique value, which is 64 characters long. We can then use a hash value to verify that the original contents were not modified. So for instance, if we added a single space to the plain text message, it will then generate a completely different hash value. So let's take a closer look at the SHA family hash functions. The different variations of SHA hash functions are distinguished in the number of bits they use for the hash value. So for instance, SHA-256 is a 256-bit hash. In computing, the bit is a single unit of data, and 8 bits equals a byte. A byte represents a character such as a letter, number, or symbol. So with a little math, we can calculate the length for the specific SHA hash. A SHA-256 hash is 32 characters long, a 384 hash is 48 characters long, and a 512 is 64 characters long. So using the OpenSSL command, we can generate the SHA hash values. In this example, we generate the SHA-256 hash value for the phrase hello world. I generated the SHA hash values for SHA-256, 384, and 512. I don't expect you to be able to read them, but you can see the differences in the length. As you can probably tell, the more the hash bits, the more secure the hash value. However, the higher the security, the more the computational and memory cost is required on the system.
So now we're going to give you a quick overview about quantum computing. So I think one of the best ways to describe quantum computers is to compare the classical bit with a quantum bit. So in classical computing, we all know it's either a 1 or a 0. But in quantum computing, it's a bit different. The bit is then replaced by a quantum bit, otherwise known as a qubit. So the qubit is geometrically represented by the Bloch sphere, and every point on this sphere, every point on this surface represents a possible quantum state of a single qubit. So mathematically speaking, the simple equation that we have right there near the Bloch sphere is the qubit quantum state. It's a linear combination of a 1 and a 0, or as a superposition of a 1 and a 0. So the coefficients alpha and beta are the probability amplitudes of the qubit collapsing either to a 1 or a 0 when it's measured. Anyhow, let's look at some of the properties of a quantum computer that are used as advantages over classical. So here we have a picture of a typical quantum computer, which looks like a golden chandelier. So when you see these types of images, you're often looking at a superconducting quantum computer, which runs at temperatures at absolute zero. So companies like IBM, Google, AWS, and Rigetti are already developing these types of computers. Other types of quantum computers that are based on trapped ions, neutral atoms, photonic-based qubits, and even Microsoft Majorna qubits. So let's focus on the 3 quantum properties that make a quantum computer so powerful. So the first one is superposition, as we talked about. It allows the quantum computer to process multiple possibilities at once, allowing them to process many inputs simultaneously. Next, we have entanglement, which allows qubits to be entangled, where the changing state of an on qubit immediately changes to the state of its entangled partner. So this results in faster and efficient processing of information over classical computers. Entanglement also helps in error correction by protecting the quantum information from decoherence. And lastly, we have interference. So quantum systems can be represented as waves. So using constructive and deconstructive interference, quantum computers can use this property to amplify correct solutions to the problem while simultaneously canceling out the incorrect ones. So as a result, interference boosts computational accuracy and faster calculations. There's also one thing to note. Quantum computers were never meant to replace our desktops. They were meant for solving complex problems that require large calculations. So just like our classical computers, quantum computers are useless without their algorithms. So 2 quantum algorithms that are basically driving the post-quantum race are Shor's algorithm and Grover's algorithm. So first is Shor's algorithm, which was developed by Peter Shor in 1994. This algorithm leverages superposition and entanglement. So this algorithm is great at finding prime factors of large integers. The most popular cryptographic algorithm that we use today, as I mentioned before, is RSA, which is based on prime factorization, which is broken by Shor's algorithm. So on this graph that I provided, it shows us the significant speed up in the number of operations required for integer factorization between the best classical algorithm and then Shor's algorithm. So on the top red line, it shows how fast classical computers will break any prime factorization. And then at the bottom blue line shows how fast Shor's algorithm breaks it. And as you guys can tell, there's a big difference. So in simple terms, Shor's algorithm reduces the time to break RSA keys from billions of years to weeks or even less. And then next, we have Grover's algorithm, which was developed 2 years later than Shor's algorithm, but it was developed by Love, Kumar, Grover. So just like Shor's algorithm, it leverages superposition, but in this case, it also leverages phase interference. Grover's algorithm provides a quadratic speedup over the classical algorithm. So we can look at this chart over here, and we see that we have n reduced to the square root of n. In the case of Grover's algorithm, the time to break a key from many billions of years to fewer billions of years using a brute force attack. So in the case, it just weakens AES instead of breaking it. Here I have provided some post-quantum encryption standards which were selected by NIST. NIST effort to develop these quantum-resistant algorithms began in 2016. Experts from dozens of countries submitted 69 eligible algorithms. NIST then released these 69 candidate algorithms for experts to analyze and to crack if they could through multiple rounds. I'm not going to go into all the technical details of each one, but you'll notice that the lattice-based algorithms are very popular among this. So first we have the ML-Chem, which was formerly known as Crystal's Kyber, and it's used for asymmetric encryption. Then we have ML-DSA, which was formerly known as Crystal's Dilithium, which was used for digital signatures. Then we have SLH SSA, which was formerly known as Sphinx, and that's used for digital signatures as well. And then we have FN-DSA, which was formerly known as Falcon, and that is also used for digital signatures. I'm not going to pretend like I understand all the math behind these algorithms, so here they are. So there seems to be a lot of hype over quantum computers in the news. We know we have some that are real, and then we have some that are misleading. However, there are many companies making large investments in progress with their roadmap for reaching fault-tolerant quantum computers. So it's very important to improve the security of our systems with PQC algorithms. So just to summarize, our existing classical encryption methods are at risk going forward. So although there are mitigations for some of the algorithms, for instance, using larger key sizes, there also is a downside, because using larger key sizes can impact performance due to the increased computational workload.
So now that we covered PQC and quantum computing in general, we can take a look at a couple services and see how we can implement PQC to help secure them. So we'll first look at the SSH protocol and then HTTPS, but really TLS protocol. So SSH, or Secure Shell, provides a secure remote logins and remote command executions. We see that all three types of cryptography are used in an SSH session: symmetric, asymmetric, and hashing functions. So one thing to note, our characters Alice and Bob that we used in our previous slides are now replaced with the client and server. Instead of Alice and Bob exchanging messages, or SSH client, known as Alice, is exchanging messages with the SSH server, formerly Bob. So we start off with the SSH client starting a connection with an SSH server. These sessions are established through a sequence of exchanges between the SSH client and server. So once the TCP connection is established through SYNAC handshakes, the client and server will exchange the version information so that they can see that they support the same version. Then the algorithm negotiation phase starts, which determines which algorithms they both support and should use. If they don't have an algorithm they both support, the exchange will end up failing. Then we go into key exchange phase, where it will generate a shared session key for the subsequent symmetric encryption. Once the service request is issued, the SSH will then be established. So this entire diagram is generalized, but all three cryptographic types are used and thus have the opportunity to be hardened with PQC algorithms. In particular, the algorithm negotiation and key exchange phases. So now let's look at TLS with HTTPS. It follows a similar sequence steps between the client and the server as the SSH protocol, including the use of all three types of cryptographic algorithms. The transport layer security, TLS, protocol encrypts data to protect it from unauthorized access from HTTPS. HTTPS uses TLS to encrypt communication between browser and the web server. We start off with the client or the browser initiating a connection with the web server. Once the TCP connection is established through Synapse, the client sends a client hello message to the server where the client server exchange information such as version information, cipher suites, and a random number. The server responds with a server hello message that includes the selected cipher suite and server certificate that the browser will then verify. Then the client key exchange and key generation phases generate a shared key based on the random number provided in the client hello message. Then the changed cipher spec message determines the the nude symmetric key and starts the TLS session. And finally, the TLS handshake ends and the HTTPS session begins where the application data is encrypted. So just like the SSH protocol, the TLS protocol needs to be updated with PQC. TLS is used by other services such as LDAP and email, especially when start TLS is used. So how do we implement PQC on SSH and HTTPS? Luckily, there's an open source project that helps with that. All the complicated cryptographic parts are provided through the liboqs, or the Open Quantum Safe System Library. The liboqs is a library of post-quantum algorithms and an API to access them. Existing infrastructure tools that we rely on, such as OpenSSL, OpenSSH, can be compiled with liboqs to provide PQC algorithms. So now we're going to walk through enabling PQC on OpenSSL. So our building environment consists of a virtual machine running Red Hat 9.5 with a minimal install, Git, GC dev tools, OpenSSL 3.2.2, plus the Devel packages. The steps for enabling PQC on OpenSSL are building and installing the liboqs library, building the OQS provider, then you would want to configure OpenSSL with OQS provider, and then verify the configuration. The OQS provider is a plugin for OpenSSL 3 that adds supports for post-quantum cryptography algorithms. Starting in OpenSSL 3, providers were introduced as a plugin system for dynamically loaded cryptographic algorithms. The Open Quantum Safe project created OQS provider, which relies on liboqs library. So let's walk through the liboqs build and installation steps. We first start with creating the build directories for liboqs. Then we download the liboqs source files from liboqs Git repo. Then we will set the environment so that we create shared libraries and install it to the system directories. And finally, we call make and make install to build and install the libraries. So now that we have liboqs installed, we will build the OQS provider library following a similar procedure that we followed for liboqs. We first start with creating the build directories for liboqs. Then we download the source files from the Git repo. Then we set the environment with the path from liboqs. And then finally, we can call make and make install to build and install the libraries. So after we install the OQS provide shared library and include the file, we need to configure the OQS provider in the OpenSSL configuration file, which is located in the /etc/ssl/openssl.cnf. We define the OQS provider and activate it as secure. So now that OpenSSL knows about OQS, let's verify it using the OpenSSL list providers command, which gives us the OQS provider info. OpenSSL also provides options to list various algorithms. Here we run the OpenSSL command to list key encapsulation mechanism, or KEM. We can see that the MLKEM is supported now. And one last check, let's list the key exchange algorithms. We can see the MLDSA and Falcon. So now we will be walking through building the PQC in the Apache web server using mod SSL. Since we already have OpenSSL enabled with PQC, the Apache can leverage that with mod SSL. Mod SSL is an Apache module that provides cryptography for secure web connections using SSL/TLS protocols, relying on the OpenSSL toolkit. So similar steps as the OpenSSH, we will install the Apache web server, enable the MLKEM, and then you'll want to test your HTTPS on the Apache. So now let's enable the key encapsulation mechanism algorithm in the Apache web server using the SSL OpenSSL configure command. Here we are using the MLKEM since it's supported in the latent versions of major browsers. After we start the web server, it should accept and support the new PQC algorithms. So now let's test the PQC connection using Chrome. As we can see, the connection is using the PQC algorithm. To tell you through, enabling PQC algorithms can be a bit underwhelming. Everything feels the same. You visit a PQC web server or PQC enabled service, but you know that the service is secure. Here, here we have a screenshot verifying an SSH session with PQC enabled. Even when OpenSSH enabled with PQC algorithms, it feels the same. But we know that quantum resistant, which is what we want.
So we only covered 2 services, but there's many more that will be vulnerable to quantum attacks. Firstly, I have PKI, which is the public key infrastructure, just like Marie mentioned with the asymmetric and symmetric encryption. Then we have blockchain and cryptocurrencies, and then we have email using the PGP and the GPG encryption. Also, popular messaging apps like WhatsApp, Signal, and Telegram use ECDH. And although these are currently sufficient right now, they will be compromised when quantum computers arrive. So thanks to a project known as the Open Quantum Safe project, and specifically the liboqs library, we're able to start testing and migrating our services to quantum safe algorithms to prepare for quantum threats. So I compiled a list of companies that are already supporting PQC algorithms. So some notable ones we see is Mozilla, Google Chrome, Amazon, and Cisco. So what are the next steps after learning what PQC is and knowing the quantum threats that are coming soon? So knowing that the quantum threats are coming, there's no need to panic. There is still time to, implement these PQC algorithms. So once then we start testing with the PQC implementations and configurations, practice your own crypto agility, and then start testing your own PQC today. And I'd like to leave you all with one last quote, and it's to encrypt like it's 2030. So I want to thank you guys for your time. We have our emails right there if you would like to reach out to us. And yeah, thank you.
Do we have any questions?
I saw his hand. Yeah, I think it does.
Thanks for the talk. I noticed that when you're listing the post-quantum algorithms that you listed asymmetric algorithms. Are there any symmetric post-quantum algorithms being developed? And if not, is there like a difference, with between classical and post-quantum asymmetric versus symmetric encryption?
Well, with the symmetric encryption, I don't know if there's I don't know any top of my head of the PQC, but the second part of your question was the classical, what was it again?
So I'm just wondering if because in classical encryption, there's symmetric would be used if there's something you need faster speeds or whatever. Is there a similar thing with post-quantum encryption, or is asymmetric quote unquote fast enough?
Yeah, I think, off the top of my head, I don't know, and I'm sorry.
Yeah, so first, with classical encryption, if you've been following it for a long time, you'll notice that the key sizes keep growing up because it's only computationally secure, and that as the classical computers get faster, smaller keys can be broken just by them.
Yeah.
So is there something similar with quantum encryption? I guess we don't necessarily know what the trajectory of quantum computers will be, but we have to keep increasing key sizes, because what that gives you also is this capture now, decrypt later problem.
Yeah.
Even if it is quantum safe, if the quantum computers get even faster, right?
So, wait, what was your question again?
Well, so is there something similar where today's quantum safe algorithm? Well, first of all, we don't know if some new quantum algorithm will come out, but also if the quantum computers, once they exist, start
Oh.
getting faster the same way that classical ones have?
I mean,
And then will you still need larger keys for those quantum algorithms?
I would assume so.
Yeah.
You know, as time goes on, obviously there's
Yeah.
going to be more advancements within the
Right.
quantum computing. So I just would say, you know, keep up to date
Yeah.
as long, like right now for classical encryption, keeping up to date with this quantum computers is something like you have to stay in the know.
Yeah, well, one other thing is, three of the four algorithms were for basically for hashing, right? So when you do the SSH exchange, depending on your settings, you may also be using the crypto to verify that you're connecting to the right host, avoiding man in the middle. Same with TLS.
Yes.
So would you have a quantum safe algorithm for that would be included in for example, the OpenSSL setup that you showed?
Yeah, you know, the library we provided, the liboqs, is a library with PQC algorithms. So,
For both?
So if you want to look more into that, I would suggest you to,
Right, because that's, and then like there'll be a way to sign the keys, just like with regular current keys to validate websites and SSH servers and stuff, okay.
There's nothing, you never get something for nothing in life. How much slower is using liboqs than using, say, elliptical key cryptography nowadays?
Wait, can you repeat that?
I'm presuming that using liboqs is slower because you're doing a more sophisticated, computationally intensive calculation. Have you measured how much longer it takes to, say, transfer a large amount of data with HTTPS with liboqs?
So with liboqs, it's a library with many algorithms. So to compare that with, wait, what were you comparing it? You said liboqs with.
I'm presuming, which could be false, that liboqs is performing a longer, more sophisticated computation, which is still basically calculationally intractable without a quantum algorithm. But are those algorithms just different, or are they longer as well, so that they, would encrypting your disk, another thing you could try and discuss in a talk like this, would that just be intractably slow if you used liboqs to encrypt and decrypt the storage medium? Is liboqs actually being used to encrypt, could I, on my laptop,
Yeah.
I mean, yes, it's possible, but would it be feasible?
Well, I was just going to add on to that. A lot of the initial work with post-quantum encryption is focused on the asymmetric stuff right now, because that is has been identified as the most vulnerable to a potential quantum attack. As was mentioned earlier in the slides, I think that even though like AES is theoretically is vulnerable, the attack profile basically as the key size grows still could possess a pretty big, like you could just keep growing the keys and that would be some mitigation. So they are developing symmetric quantum safe algorithms. However, I think a lot of the focus right now is on the asymmetric for like the key exchange, because that seems to be the most vulnerable.
Yeah.
Oh yeah, of course you could do all your encryption like that, but it's still going to have the same problem that classical asymmetric has, where it's just not super fast. But I think back to I am interested about as well. What are the performance implications of the currently available post-quantum algorithms, if you know about that?
Yeah. I don't really know. But after you could come see me, and I'll try to figure out an answer. Yeah. I would say I was really into cybersecurity, and then I remember in 2020 during the pandemic, I actually took a quantum computing course, and then from there I just learned more about it and became more interested in it.
Have you seen a show called Devs?
Yeah.
What's your opinion on Devs?
I thought it was pretty cool, like just seeing it, but then like some parts were just like kind of crazy, like just like the plot, like the storyline with it. But like that like also like made me more interested in quantum computing because we both took the class together. So yeah.
So then, because you already answered why you got into the quantum cryptography, how about you?
Oh, I was also interested when we took the class during the pandemic as well, because I'm pretty sure it was with the coding school. So, and it was taught by like MIT graduates, so nice.
I mean, just as a demo, if it were me, I would just pick a giant file. I would encrypt it with RSA and measure the time, and I would encrypt it this other way and measure the time, and then the same way with disk decryption. So it should be.
regards to that. The performance implication question is a little bit like it can kind of be meaningless at some point because a lot of we have like so many different encryption algorithms available today, but part of the reason why we almost always are using some variant of AES is because we have hardware optimizations for the AES encryption. So really, you're not going to get anything that is like as fast as that, as fast as the stuff we've optimized hardware-wise. But if we're moving to a more post-quantum safe world, inevitably we'll be developing hardware acceleration for that kind of stuff to bring it up to speed with what we would expect for a modern encryption hardware.
Yeah, and even with hardware-accelerated AES, you can see the performance difference if you encrypt and decrypt a full disk. I mean, if you boot from an encrypted disk, you can see at the startup it takes longer. So, Well, that was a super great talk. Oh wait, one more question.
So I'm jumping in. I missed the whole talk and I lament it. I haven't seen this topic in about 20 years. I was researching it in grad school at the time. But what have you, and it was already commercialized to an extent. I remember Magic Q. There's already experiments like under, I don't know, remember, like in Switzerland under Lake Geneva, they had like fiber optics that had done like some quantum encryption already. And like Magic Q in Canada and others had already like commercialized like for banks for transactions, quantum encryption keys and stuff. But what have you seen from like maybe like online regarding like quantum encryption schemes from like adversary state actors? There's a lot of that online, but I just don't know what's the state of that. Have you seen any of that?
No,
Like
I
what's,
haven't.
no? Like if what on what's the, maybe something to look into. I don't know.
No, yeah.
'Cause I know they claim a lot, but it's hard to prove these things, right? It's like it's hard to take these things at face value, right? Just look at it in a paper, but so anyway.
Thank you.
What's coming next, right?
No, yeah.
Yeah. I mean, I know they're working on hardware optimizations for some of these lattice-based algorithms, but hopefully by 2030 we'll have it, if not sooner. Because I mean, I think people have been using at least some lattice-based algorithms. I think they're used like in some real-time devices like cell phones already. So I don't know if what hardware is used to help accelerate that, but if it's not, it's coming for sure.
Well, thanks to you guys for a great talk.
Thank you, everybody. Thank you. I really appreciate it.
Hello, hello. Ah, there we go. All right. Yeah, that's fine.
Yeah, and it sounds clear, it's not going.
Yeah. Unless I do this.
Well, he was holding it like that,
Yeah. Feedback or
No,
distortion.
vocal noise,
Yeah.
from his mouth, So,
sparklers. We lost him. No!
Call for backup.
This just in. We have a wild police chase involving a penguin and sparklers.
That's right, Angela. We're going to Noah in the JB Chopper, where he has eyes on the suspect.
Chris, the penguin who has been identified as Tux is running through Burns Park. He's running directly towards fast-moving traffic. I don't think he's going to get out of this one, Chris.
That penguin's a slippery character. I bet he wishes he could fly right about now, Angela.
He sure is in a waddle of a predicament.
They're gonna wipe that pin grin right off.
We have a new development. It looks like the cops have him surrounded.
Police, turn around! Really? Popsicles?
Finding where you fit. LinkedIn knows how.
The time has come. You are a team player. You reach for the stars. You want to change the world. Join us on a mission to Paleo.
The future is now, and we want you to join us now. At System 76, we give back to our devoted fans by taking our passions to new heights. So to up our game, we left our boring families behind and went to space. Now we're looking to recruit only our most loyal fans to join us in exploring Thaleo. Because anyone else would be a waste of oxygen, which we have plenty of.
Oh, terrific.
Check out our entire line of computers, meet the team, and explore Thaleo. Come be part of our important mission at Superfan.
I'm part of the mission.
We're all excited to bring you out to our imaginary corner of the universe, Thaleo, also known as Denver. Even our accountant is excited to bring you here.
We're doing what now?
You're playing coach.
Kate, did you budget for that? Kate?
If you're one of the lucky few to be recruited to our space crew.
Kate? Kate?
You'll enjoy a week
Two-night stay.
in Denver, space games with the squad, event-exclusive goodies, a roundtable discussion with the engineers and CEO.
Hey!
And some added surprises. We're now recruiting our space crew for Superfan. Now, So start your enlistment today.
All right. Can you guys hear me? All right, I'm on. Excellent. All right. Yep. As you said, I'm Carl Rochelle. I'm the founder and CEO of System 76. If you don't know about System 76, we're a 20-year-old Linux hardware manufacturer, which is kind of shocking to even say. 20 years in is pretty amazing. Yeah. Well, thank you very much. We couldn't be here for 20 years if it wasn't for the open source community and all of your support. So thank you for that. And all that support and also enables us to do some really incredible things in open source, like build a desktop environment from scratch. Incredible, maybe crazy at the same time. So I'll tell a bit of a story about deciding to make Cosmic DE or to make it a desktop environment. It goes back to, I think, 2000, let's see, 11, 10. So it goes back to about 2020. Just before that, I think it was, gosh, I'm trying to remember the release, but essentially what was happening is our support team was getting all these calls from customers saying, I'm using Pop! OS, how do I install i3? I'm using Pop! OS, how do I install Sway? All of our developers, every one of our developers was using i3. They weren't using GNOME on Pop! OS. Then I fly out to Mountain View, California, and at the Google campus, and we go to the Open Firmware Summit, and half of the users there, or half of the customers or attendees, were all using i3. And we realized, okay, this is enough evidence. We're not delivering what our customers want out of the box in Pop! OS. So that's when we decided we were going to make a dynamic tiler, or auto tiling as we called it in Pop! OS. We built a GNOME shell extension called Pop Shell. And our engineers couldn't stand JavaScript, so they wrote it in TypeScript, and we built an automatic auto tiling UX into the GNOME shell. That's when Pop! OS, and that first release is when Pop! OS started becoming much more popular. So there was a response from users. By listening to them and delivering the things that they wanted, it's the calls to our tech support saying, how do we install this thing or do this other thing? Because when you shipped me my computer, it didn't have what I wanted and didn't do what it needed. But now you're doing the thing that we were asking for. And so those calls declined, and the use of Pop! OS, not just from our customers, but from just the general public, increased considerably. It was something like 4 times when we released Pop! Shell. Then we went through a number of releases for a couple of years where Every 6 months, we were updating Pop Shell for the new GNOME release. Essentially, we weren't spending all those engineering cycles and all of that time adding a lot of value. We were adding features incrementally, but a lot of the work was just continuing to make Pop Shell and tiling work on top of GNOME. That's not the most satisfying use of your time, or and like I said, we're just keeping up every 6 months instead of adding new things all the time. And there's just the clashes that when you're trying to do something different that upstream doesn't necessarily think is right for their users, end up creating. This wasn't a type of UX that GNOME was very interested in delivering in the way that we wanted to deliver to our users, and that's okay. That's every project has their prerogative, and so we weren't. So it wasn't like we were ever going to get it upstreamed. It just wasn't going. That wasn't going to happen. And then GNOME also wanted to remove some theming functionality that we thought was really important for Pop! OS. And as these things came together, we realized, well, we probably should figure out a better way to deliver our Linux operating system to users. So our initial discussion started in August of 2021. We put together this pros and cons list, and I think there were 4 things. It was like continue doing our GNOME shell extension. There was write a Mutter plugin, and we wrote a small plugin and started working with that, but it kind of had, it would be difficult to maintain. We wouldn't have full control over the experience with the user, and we might have the same kind of thing, issues trying to collaborate with upstream when you have different vision. We could have forked GNOME Shell. That was another one of the options, but if you fork GNOME Shell, then you've got users that are coming, it still feels like it's GNOME, and then the extensions don't work the same, and so that's not a great experience for users either. And then there's this final option: how about we just write the whole thing from scratch? Well, that's what we decided to do. We took the hardest and the most expensive approach. We said, well, that's probably the right one. So we had a team summit in May of 2022. That's where we all got together, all the engineers, designers, tech support, technical writers, the whole team got together, and we discussed our vision for the desktop, which is what we'll get into. That's where it started. And we also realized at that point, well, we're going to have to choose a toolkit to build all of this in. So we built panels with GTK, and we had a lot of experience with GTK. We're used to it. We're used to the Rust bindings. We knew we were going to write our desktop in Rust. As a company, we adopted Rust, I think, 2017. And from that point forward, everything we wrote was in Rust, everything new. So we tried GTK. Then we really like Slint. Slint is also a great toolkit for writing Rust. We also took a look at Flutter briefly and considered that. In the end, we went with Iced because we wanted a pure Rust stack from the bottom all the way up, and we liked Iced licensing, and in that I believe it's MIT licensed. Slint kind of has a dual license for commercial and open source, and we didn't want any of our users or people developing applications to have to make a distinction between those two. We wanted it to be just a very liberal license, which is why we chose Iced. We build libcosmic on top of Iced. You can think of libcosmic as like libardueta. It's the library you use to build applications for Cosmic. It has, and choosing to do this, it means we had to write all of the widgets. There were 0 widgets for Cosmic. We had to write all the widgets. And Rust at that time, of Rust windowing, didn't even have text rendering. So we had to write text rendering and all the implications with that, with right to left languages and all the stuff that people far more in depth than me realize how complicated it really is writing text rendering. But the cool thing about that, and the cool thing about taking this approach, is that for the last 3 years, we've been a central part of building up the Rust's windowing ecosystem. So today, whereas you couldn't 3 years ago, today you can write full and complete apps in Rust, and that's thanks to a lot of the work that we've done along with the community. The Cosmic Text is basically the standard text rendering library for Rust. So we started out with design experiments. These were just mock-ups that we did in Figma. And one of the cool things about starting from scratch is that, and being around for a while, is that, you know, we were around since 2005, so we saw the invention of the iPhone and iOS, we saw Android, we saw Chrome OS, and we've also seen how they adapted over time. But a lot of desktops, you know, were started before all of these devices had different screen sizes and all these super high DPI displays, and responsive design wasn't important, and now it's extremely important. So we could start from scratch with these ideas in mind. We wanted applications that were responsive but felt natural to use. And we had some ideas about how to do that. We mocked them up in design experiments. You can see here on the left, we call that the nav bar. And at the top, there's a big button that says favorites. This is very early stuff, but it gets prettier. So the idea is that you can expand and contract the nav bar, but if you move the window in and out, it'll do so automatically down to a single column. And then you have your normal content window and the preview window. And we haven't written a PDF reader, but we mocked one up. We also mocked up like a media player, a Spotify style player, because we wanted to make sure that the UX that we were developing could be used across a number of different types of applications. Cosmic is a professionally designed platform. It has a design system that describes how button layouts work, how text inputs work. There's a lot of color theory applied to the theming system. We do a lot of calculations to ensure that there's always contrast, regardless of what colors you're choosing to set your background colors and other things to. So we'll automatically adjust text to reach AA contrast at least. And now these are the real apps. You can see it's actually pretty close to what we envisioned a few years ago. We have the navigation bar on the left, the main content, and then preview. I'll show you some cool features in Cosmic Files because we have also a gallery mode that's really awesome where you can go through all of your pictures in a nice, pretty gallery. But then you can see it collapsed there as well, where in a single column, you can open the navigation bar or open settings or preview windows, all from a single column all the way up to full size. So engineering Cosmic. So our goals in engineering Cosmic was that it's modular, compatible, and composable. Modularity means that the individual components that we use to create Cosmic don't have to be there to use them. In other words, Cosmic has a panel and a dock and applications in a compositor, but each one of those are their own application. It's not one big application running the entire desktop. Everything is its own process. And there's very light or no dependency between one process and another one. So you can have an applet in the panel that's maybe is for monitoring CPU usage. But it has no dependency on any other application in the panel. Compatible in that we work very hard to work with upstream and on Wayland protocols and XDG and free desktop to ensure that the things that we're doing are compatible across Linux desktops. And composable in that you can put each one of these pieces together, and our settings system is in a nice tiered text files format that's very easy to use and very easy to develop, and you can compose a desktop from all of these pieces to make all the way up to a full desktop environment like normal KDE. Cosmic Panel. So Cosmic Panel is the application that runs the panel at the top of your screen or a dock at the bottom, or you can rearrange them in any way that you like. In our settings, we have a panel and a dock, but those names are actually arbitrary. You can have, and we only have 2, you could have 16 panels if you want. You can configure it in any way because who knows what you might want to put together. The panel is a nested Wayland compositor, and applets are just standard XDG shell clients. The XDG pop-ups are forwarded to the host compositor, and writing new ones can be done in any Wayland native toolkit. So each button that you see at the top there is an independent application running on its own, and it can be removed and added to the panel. They can also be sandboxed, and if one crashes, it can't affect any of the others. You can run system monitors. People are making applets already, and for community contributors are. Things like weather and networking. Cosmic Panel is so powerful you can run Celeste inside of it. You can run Doom in Cosmic Panel. Okay? Yeah, it might sound crazy, but when you think about the kind of things you can do by applying panels that you can lay out anywhere on your screen, in any orientation, at any width, maybe somebody wants to create something with a wide panel that has videos that will play in the side. And there's no reason not to. It can float away from the side. You could have graphs running inside of the panel. It's essentially limitless what you can do in the way that you can lay things out and build things with the cosmic components. And that's kind of the point. Yeah, it's a desktop environment, but it can be any other type of device that you can think of. Cosmic Comp, so we wrote a compositor for Cosmic as well. As I said, it supports various protocols like WL namespace, and we work a lot upstream to ensure that what we're doing is Wayland compliant or compatible. There are Cosmic protocols. These are custom protocols, but there's a constant effort to upstream any protocols that we're working on. And most of them are based on existing protocols or extending them so that as those become mature and are adopted, it eases the transition. The goal is to make all these optional and know their private APIs. Cosmic Config, as you can see here at the bottom, these are the configuration files for the panel. And at the top here, this is the configuration file for the applets that are applied to the panel. And it's as simple as, like you see there, I guess I can look here. The Workspaces button is on the top and left. The App button is on the top and right. And on the right, there's the Power button, Time, Bluetooth. Each one of those is a separate application, a separate applet. And just by listing them by their name, they'll appear in the panel. It's a library and optional daemon. There are atomic operations. It's file-based. It's tiered and versioned. We're currently on version 1, and throughout all of our development, we haven't needed to do anything that wasn't backwards compatible. So there isn't a version 2 yet, but it's version just in case that kind of thing happens. Cosmic, this is part of composability. It's very simple to lay out what Cosmic will look like inside the configuration files beyond what you can get in the settings. And one of the ideas here, we're going to get into, is as perhaps a distribution. Maybe the applets you want for your distribution should be laid out in a different way than Pop! OS thinks they should be laid out, or the panel should look different or be in a different orientation. It's very, very easy to set up, package, and ship to your users. Cosmic is a platform. For developers, use what fits your needs. Develop new applets or shell components for what's missing or different ideas that you have that you want to explore with your users. For distros, you can adopt different configurations, ship different applets or components, and you can brand Cosmic so that when you're running OpenSUSE or Fedora or NixOS and your users download your operating system and install it on their hardware, it looks like your operating system and your brand. And for end users, we all get to lay things out and make the experience what's best for our workflow, the way workflow and the aesthetic that we prefer. Do you guys remember this?
So we could just daisy chain up to 127 USB devices here. That's an everyday task. Let's plug it in. It's going to say, hey, I see you've plugged in a new device. And it's going to load in the appropriate drivers. You'll notice that this scanner build, whoa.
We'll leave that pause here. Okay. So yeah, let's do a live demo, right? All right. Okay, so this is the Cosmic Desktop. And the first thing I'm going to do is rebrand this desktop for OpenSSL. So let's let's give it a go here. After we do that, we're going to go through some features as well, some of the unique things about Cosmic, but I think this will be fun. So we're going to go into Appearance. I'm going to import a theme. And that looks pretty nice. SUSE, did you guys know that August of last year they released their own font named SUSE? So we can adjust the font. This wallpaper doesn't look right, so let's try a new wallpaper. Now we're starting to look a little bit more. Let's see, let's do a light mode too. Import. There we go. And now we can, let's start up some applications. There's Cosmic Files, the Cosmic Store. Might as well do a text file. So you can see, you can adapt the appearance to feel like it fits with the brand that you've made. Now, that's one thing, and it goes a long way to giving your users a cohesive experience, because they're not going to your websites and then and you have these wonderful SUSE brand colors with these nice dark blues and greens, and then you download Tumbleweed and you install it, and it's blue, and it's light blue, and it doesn't feel like the place where I just downloaded from. That's not it's not a great user experience, I don't think. I think that consistency really matters in being able to deliver a consistent experience. The other thing about distributions is you are the closest people to your users. You are the ones listening to the feedback from your users and understand the things that they use their computers for, what matters to them, what pain points they have. Not all users are the same, and not all distributions need to be the same either. We can have unique experiences, we can build unique experiences. So let's say, for instance, like here I have it set up with, we've got a top panel with our workspaces. We've got our application library here, and I've got these, again, each one of these is a separate application running inside of the panel. We have our different applets there. We have an app tray here. We have a minimize feature down here, embedded here too. Let's just say that through user testing or experience with users, OpenSSL thinks that this top panel, this bottom panel, it's probably not the right layout for our users. Let's try to deliver something different. So we can we'll go to the dock. We're just going to turn the dock off. We're going to go to panel. We're going to move it to the bottom. Okay, it's different. It's not great, but it's different, right? Well, let's make it a little bigger. Okay, we're getting somewhere. Let's tell you what, let's move the time to the left. Let's put this app library and workspaces button over here. Let's see. I don't have a way to launch applications, right? But if I add an applet, okay, I'll add the app tray and minimize windows. That's not in the right place. Let's move the app tray over here and minimize windows. And now I have a brand new OpenSSL layout with the bottom panel. It has all the same functionalities, that I had with two panels. And maybe that's a better experience for their users. But or for you, if you want to change it to what you'd prefer. I became a bottom panel guy all of a sudden. I used to have the top panel in the dock, and now this is how I run my computer, and I don't use as many applets. Like I don't use input sources. So for me, I just go in and remove input sources. I have accessibility in these days because we're doing a lot of accessibility work. And Jill, thank you very much for helping me. And there's another gentleman that helped me today. We went through accessibility features, so that was very helpful with our desktop Zoom features and screen reader. But that's the point. If you don't use lib input, or sorry, if you don't have input sources because you're not using multiple languages, you can just remove that from the panel. If you don't use accessibility features, you can just remove it. If you don't care to have Bluetooth on the panel, you can remove it. Because I can go into settings, like maybe I don't need to add Bluetooth devices or switch to them often. So if I go and remove Bluetooth, that's okay because I still have it in settings. It doesn't need to be in my panel all the time, so I can just I can access it from the settings if that's what I need. Keep my panel a little cleaner, perhaps. You see the media control there. That's because we had a video playing, but we have the option to add media controls to the panel automatically from the volume outlet. So you can kind of start imagining just the power of a composable desktop where you can adapt its layout and where everything is. My next one, do we have any NixOS folks here? All right, how's NixCon? Fantastic? Excellent. Well, because NixCon was here, I wanted to do a Nix theme as well, or Nix branding. So I pulled these from the website. I couldn't find branding docs, so this is my best attempt, but here we go. Go to a light mode. And you see how all the applications adapted to the new theme automatically? It's pretty stunning. And in Nix, I decided for some reason, I thought, Nix seems like maybe more square, whereas OpenSUSE has kind of like a rounded, semi-round elements. So I set the theme to square. So with square, all the elements change to square instead of like round. Right now, all the text inputs, toggles, sliders, they all adapt to the different size. So you can also have more control over the radiuses throughout your desktop as well. But then this wallpaper isn't quite right for Nix. So let's switch to this one. Now we have rather beautiful Nix desktop. And this one looked really pretty to me in the logout screen. I thought it was pretty nice too. And then maybe Nix wants to do something completely different and wilder than OpenSUSE. So perhaps we want to go back to a panel on top. But maybe the panel should be floating. Maybe it should be really small. Maybe it shouldn't extend to the end. And then perhaps we should, there we go, put them back. And then enable, maybe we want the dock. But the dock should be maybe on the left. Maybe this is the kind of experience that NixOS wants to provide out of the box. No, I have no idea. But the point is, you're close to your users. You have the closest relationship with your users. You get the fastest feedback loop. It's great to be able, we want to provide a platform that enables you to respond to that feedback and adapts your user experience to the things that you're learning from your users. All right, let's look at some features. So one of the key features in Cosmic is tiling. So that's how we got started down this journey in the first place. So just with the click of a toggle, all of our windows are tiled together. As we launch more applications like, let's do the store. They'll automatically tile into place. I can use super and arrow keys. You can kind of see here, you see the highlight around the windows moves as I move focus. I can grab a window and move it. with my keyboard into any other location that I want to put it. I can also swap windows. So if I want to move my files and swap it here, we've just swapped our windows. I can also stack windows. So if I want these two on the left stacked, I can grab this window and put them together. And now I have windows inside of tabs. Where am I? There we are. So, and then I can pull that window out of the tab. Everything that I could do with my keyboard shortcuts, I can also do with my mouse. I can pick up the window. I can see where it's going to land when I drop it. So there's no confusion about what position my window is going to take once I let go of the mouse button. In Cosmic, you can have a tiled workspace and a floating workspace. So I've decided to tile this workspace, but in the workspace below, maybe I want a couple of apps, and I don't want them to be tiled. So I don't have to have tiling across the entire desktop. I can mix and match workspaces depending on what I'm doing on the workspace and whether I want it tiled or not. Just by toggling a feature, we turn it on easily. And we have a choice here. We can choose to have all our new workspaces tiled or floating. That means as I start a new, or go into a new workspace, the next application that I launch will either launch floating or tiled, depending on my preference. So you can have it, everything start tiled if that's just your default, or you can have it start floating and then tile as you want to. All right. Of course, we have, I'm going to put this dock at the bottom because I don't know if I can handle it on the left. And let's extend it. I don't know, is light mode like destroying your eyes? Let's see. Let's go back to dark mode. Ah, this is a sigh of relief. All right. I showed you a lot of the theming, and it's really cool to be able to take the power of the theming engine and then apply it to your distribution. But you can also do so just as a user, and it's a very simple interface to do so. So we can change our accent color. We can change the background color of our windows. We can change the roundness of our buttons. We can change to compact mode, where everything's tighter together, or super spacious. Super spacious helps some users that just need where it's visual separation. Helps identify objects. It also can be good for touch interfaces if you have more space in between. We can adjust the window tint or the window hint size. We can really adjust the window hint size. We're not really into restrictions. Things can get weird, and that's okay. Yeah, if this was a free text, we can make our gaps enormous. We can make them smaller too. But the point is, there's not a whole lot of reason to put severe brackets around things. Users have different preferences, and that's good. It's also pretty cool. Oh, NixOS, I also forgot about this, but their logo is in, I think it's pronounced Vigor, but we can also change to match NixOS's font. So it's really easy, even as a user, just to get really unique layouts and colors and a feel and aesthetic that you like. Some other features in Cosmic are we have scaling. So one of the nice things about Wayland is we can actually develop really nice display scaling. And with scaling, it's not visible here because the displays are mirrored, but we can scale up to 300%, We can also scale in smaller increments. So sometimes for me, at the end of the day, my eyes are getting tired and I just want a little bit bigger text. Well, instead of having separate text size, what we do is scale the interface. That way the text doesn't go outside of its container or its buttons or other things like that. But we can do it in smaller increments of like 5 pixels. So you can get just the right, you can dial it in just right for, for what feels comfortable for you. Besides that, everything that you can do in tiling mode, you can do in floating mode. So if we switch back to floating mode, I can use the same shortcuts to move around my windows. I can also grab a window and I can manually tile it into a corner. So if you're not into the automatic tiling, you can still use manual tiling. We call it snapping. You can snap windows to the side. Other than that, essentially all the features that you would think of in a desktop environment have been built out in Cosmic. Connecting to networks, VPNs, Bluetooth, we're working on a lot of accessibility features. That's about what we have left is color inversion, color filters, things like that for color blindness. Screen readers working well and desktop zoom is working well. Power and battery has options for your modes and how soon your display will go to sleep or when your system should suspend and whether you want to disable those entirely. Input devices, we have separate settings for keyboards, mouse, and touchpad. So you can, if you want your mouse wheel to go, what is not natural? Normal scrolling, but you want your touchpad to have natural scrolling, you can set those separately. Time and date and time and region and language settings. And like I said, with Cosmic Text, also we have right to left rendering and right to left text working in Cosmic as well. And then we also have, besides setting up users, also default applications, so you can configure those. That's most of the features in Cosmic. For the main applications, we have a file browser, and in the file browser, it's Cosmic Files. We have previews, which is control and space will open the preview, so you can browse through in another way. So if you're uploading a file or a picture to an issue or to another place, it's a lot easier to get a glimpse of what you're uploading. But more so than that, we also have a gallery mode. I'm sorry, all of my screenshots are Cosmic. Because I'm taking a screenshot and saying, hey guys, we got to fix this, we got to fix this. So I don't have pretty pictures. But we also have a gallery mode. So if you press the space bar, it'll open up the gallery mode and we can browse through. Like you could imagine this being your pictures folder. And you can browse through your pictures in a nice gallery mode inside of Cosmic. In addition, we have a Cosmic Media Player, which if you were here earlier, we were playing a Blender movie. We have a text editor. Oh, where am I? Mouse is grabbing it. Text editor. We can open and manage projects. Let's see. This is a community-contributed app that was called Observatory, and it's like a system monitor app. It's pretty awesome. We have syntax highlighting and projects, and we have Git management also built into Cosmic Text. So it's pretty awesome and Vim shortcuts as well. You can enable Vim shortcuts inside of your text files. We don't have LSP support yet, but we are considering adding it down in a future release. So it'll be a pretty nice kind of basic text editor as well, a code editor. Let's see. Of course, there's Cosmic Store, the App Store. And as you can see, the applications are all responsive, as we had talked about. So if I close this, it's going to open the navigation bar. If we add the Cosmic Terminal, you see how it responded to becoming a single column application. But if I want to get back to the navigation, I can just click the navigation bar and browse to different areas inside the application. Same is true, you'll see here, Cosmic Files will close to a smaller set of files, or is responsive to moving outside the desktop. So you can imagine Cosmic being built or being used even down into a phone device. So all the applications are responsive. If you combine the panel, and you would probably adjust what applets you have in the panel, but with that and responsive applications, you could have, you very easily put together a user experience on a mobile device or on a tablet or on any other kind of device. I think that's about it. Cosmic settings and Cosmic Media Player fill out the rest of the Cosmic application suite that's there so far. We do intend to write a PDF viewer in addition, but that'll probably come in a second release. A system monitor and a few other things. So ultimately, we want everyone to have a pure Cosmic experience out of the box that most of their application needs covered. All right. So as I started with, Cosmic it's going to be the flagship for Pop! OS, and it's a great desktop experience, or a desktop environment experience on a computer or a desktop. But it's really built for a much bigger purpose. It's built not just licensed as a GPL project, but with the spirit of GPL, and that it's intended for people to take Cosmic, to adapt it, to change it, to brand it, to build your own experiences with it, whether that's for a distribution or for a mobile phone or a gaming console or any other device you can think of. It's intended to enable you to have all the pieces or the pieces that you can put together to create your own unique experience. If you think about the most successful projects in Linux, things like the kernel itself, Apache, quite a few Linux distributions. What they all have in common is that these things are what people use to build other things with. And that's what's different about Cosmic. Yes, it's for us to have an experience for our customers and our users with Pop! OS, but it's more so for the open source community to have a tool and a platform to build things with. So that's it. Thank you very much for coming. Be happy to answer questions.
Hi, I have a fantasy, and I'd like you to tell me how close Cosmic can come to fulfilling it.
I'm sorry?
I have a fantasy, and tell me how close Cosmic can come to fulfilling it.
I'd like to start.
I have used windowing systems since the Xerox windowing systems in the early 80s. I would like to do the following. I've seen your workspace, multiple workspaces, and I want to be able to tell it. So how do I make it such that the right mouse on a workspace can cause it to be renamed? So it would tell me, pop on the background for the workspace, then have a list of all the operations on it, click on mouse actions, select mouse action, and add rename workspace to mouse action, and then alakazam, that's the behavior. How close can you come to that?
Let me make sure that I'm understanding. Is the objective to name workspaces?
It's a stack of objectives. One of them is to rename workspaces, but the other one is that I want it to be such that I can have it from a background menu that click on a mouse. In other words, I want to change the mouse semantics. That left mouse selects, double left mouse activates, right mouse gives me a background menu, and then since I don't know that because I'm a new user, I want to click on an AI that says, how do I do this? It will tell me how to do it.
I see. Well, I don't know. So workspaces is interesting. Let me show you here. So if we open up workspaces, this is a completely separate application that's not in the compositor. It is, we have wrote, honestly, I wish we did it in the compositor. It would have been so much easier, but we didn't. We wrote it as a separate applications and wrote protocols between the compositor. And it's difficult because you have to have screen copy capture for all of these windows and be able to move them around. So it's really complicated. But what that does is it means that this can be replaced entirely. So while this is the workspaces experience that we're building for our users, and for the simple example of naming the workspace, that we do intend to do that, not for the first release, but probably a second release. The idea there is you can name a workspace like development, one for communications, one for something else, and then from the launcher, you can just type the name of the workspace that you want to jump to and it'll go to it. So that's what we intend to do there, but what I'm starting with. You can, yeah, you could change what the right mouse button does or the left mouse button does. And that's something that you could do today. It's what gets built into settings and is like what you would experience from first use is one thing, but what you can make out of it and what features you can add and change and modify are wide open. Yeah, well, I had the pleasure of going, there's a computer history lab in Boulder, at CU Boulder, and I got to go there a couple months ago, and it's not just a history museum, it's a working lab. So I had the opportunity to, like I said, on the next cube, and play with what was going on there and go through just decade after decade of desktop user experiences, and there's a lot to learn from history. I agree.
Sorry. There we go.
At the end, I heard you mention the Cosmic Desktop could be used for various experiences, including like a mobile phone. Would System 76 ever venture into the Wild West of creating a non-Android Linux phone?
He's going to answer the first question first.
Oh, you know, Mike? Get up there. Yeah, okay. All right.
All right. Hello? All right, there we go. I don't know. That's it. No, long term, I would like a much more liberal landscape for hardware and software in general. Our mission is to liberate the computer, and that doesn't stop at a laptop or a desktop. How long of a path that is? We've been at it 20 years. One thing we have is endurance. So if it takes another 20 years, that's fine. But what we've shaved off already is firmware, a lot of hardware design, electrical design. Now we're building a desktop environment. I don't know what the future is going to entail entirely, but every opportunity that we have where it's within our means, we will do more to liberate the computer.
So you mentioned that Cosmic is built around the applets, and I was wondering how you can get third-party applets, like GNOME has the extension store and KDE has it built into the desktop. What's the vision for that on Cosmic?
Okay, so we want applets to be able to be installed from the Cosmic store. So you'd be able to install them and then add them to your panel, or you'd probably, the UX would probably go from the store to settings, where then you can add them to your panel. That's I think what's going to happen. There are a lot of community applets already. Actually, to extend that a little bit more, our real goal is to have applets in FlatHub and be able to install them in FlatHub and then change them inside of your inside of the settings for applets. So that's how we like to. We haven't gotten packaged there yet, but so it's kind of experimental, but that's the goal. Yeah, no, I think we can do it through FlatHub.
Oh, two quick questions. One is, you mentioned that Cosmic has been tested on tablets. I'm wondering if System 76 is venturing into like making their own tablet, and what's the level of like testing and for integrating like a Cosmic environment on a tablet with a touchscreen interface, right? How that's working out, because I just see more and more people going to tablets, like from laptops to tablets. And the second question is like, you guys are very tuned into everything that's like the builder, the developer, scientist, DIY community, those now training AI. Where do you see that going into the future? Those are the two questions.
Great. For the first one, tablet is very similar to the mobile answer. I don't know, we're ambitious, and we would like to be able to have a freer, more open tablet experience, just as well as on the computer, so hopefully that's something that we can get to. With regard to AI and LLMs and how that integrates, I think there's a lot of interesting opportunities. One thing that Jill and I actually talked about is screen readers on Linux aren't great, or all right, but it's very hard to learn and hard to use. It seems like a good opportunity, perhaps, for computer vision or for MAI. That would be a kind of a dream to improve accessibility on a platform. So I hope that's something that I hope that's something we have a 6-person team building Cosmic, or 7-person team, and over time, as Cosmic grows, and if the hope is Cosmic becomes very popular and means that people appreciate what we're doing and buy Sim76 harder because that's what funds Cosmic, right? If that feedback loop works, then we'll be able to add more engineers and do more creative and more unique endeavors like that.
Questions here and there.
I have 2 questions. Number 1, when will ICC support come in, the monitor calibration tools? And number 2, for the power settings menu, do you ever plan on supporting third-party power management systems, i.e. TLP?
I can't really answer the second one because I forget. The first one, ICC stuff, HDR, we're going to be working on directly after the first release. So hopefully not too long after that. We did survey users, and they considered it quite important, so it won't be too far behind. I've been told I can't give dates anymore. Well, thank you very much, everyone. I appreciate it. Feel free to grab me afterwards.